Mixtures of latent variable models. When full covariance matrices are used with the Gaussian mixtures, even if there is no singularity, one risks overfitting if the input dimensionality is high and the sample is small. To decrease the number of parameters, assuming a common covariance matrix may not be right since clusters may really have different shapes. Assuming diagonal matrices is even more risky because it removes all correlations. The alternative is to do dimensionality reduction to clusters in the clusters. This decreases the number of parameters while still capturing the correlations. The number of free parameters is controlled through the dimensionality of the reduced space. When we do factor analysis, section 6.4, in the clusters, we look for latent or hidden variables or factors that generate the data in the clusters. This is provided by Bishop, 1999. The probability of x to t conditioning on GI is approximately by the normal distributions of mi and vi times vi to the transpose plus vi, where vi and vi are the factor loadings and the specific variances of cluster GI. Rubin and Thayer, 1982, give EM equations for factor analysis. It is possible to extend this in mixture models to find mixtures of factor analyzers. In the E step, in equation 7.9, we use equation 7.18, and in the M step, we solve equation 7.12 for VI and VI instead of SI. Similarly, one can also do PCA in groups, which is called mixtures of probabilistic principal component analyzers. This is proposed by Tipping and Bishop in 1999. We can of course use EM to learn SI and then do FA or PCA separately in each cluster, but doing EM is better because it couples these two steps of clustering and dimensionality reduction and thus a soft partitioning. An instance contributes to the calculation of the latent variables of all groups weighted by hi to the t.